everybody, welcome back. Today we're going to talk about parallel circuits. Now, hopefully everybody went through the series circuit lesson, found it understandable, found it easy to work with, and found it to be relatively familiar because we did go over that last year when you guys were juniors. This is really the crux of what we need to get across this year, though, is understanding parallel circuits. Now, as the name implies, it's usually two things running side by side, two circuits. In our applications, you could think of this like both of your headlights are operating at the same time using a similar circuit, probably powered by the same power source and switched by the high beam dimmer switch, powered by the headlight switch, and then ultimately powered by your battery. Everything kind of comes from a common power source through a usually common controlled device, and then it goes to the individual loads. And each individual load has its own designated circuit. Now, when we talked about series circuits, we talked about how you might have a resistor here, a resistor here, and a resistor here, and the circuit would have to flow through all of them. What happens in a circuit like that is you lose voltage across each load. It's called a voltage drop. So let's say, for example, we had a circuit that has a resistor here, here, and here. In this example, we would have a certain amount of voltage drop across this resistor, and then this resistor. And by the time you reach the end of the line, all the voltage from your power source has been consumed. So again, let's assume we're working with cars here. We're looking at 12 volts or thereabouts. If we have a circumstance where this is 4 ohms, this is 4 ohms, and this is 4 ohms, we would have a drop across each load. Now, we know that 4 times 3 is 12. So what we would have here is a drop of 4 volts across this load, 4 volts across this load, and 4 volts across that load. By doing that, each of these, let's assume they're light bulbs for sake of argument, you'd have a common intensity because they're all the same resistance, but they would be diminished versus running that light bulb with a full 12 volts. What we would ideally have is a circumstance where this one would have its own power source and ground source, this one would have its own power source and ground source, and this one would have its own power source and ground source. And by doing that, each of them gets 12 volts. So let's rearrange this so that we have a circumstance where we have full power and ground supplied to each one. In this new example, we can see that we have the same number of resistors, there's still 3 of them, and each resistor has 4 ohms, 4 ohms, and 4 ohms of resistance per resistor. What we have instead of our normal resistor after resistor or load after load is a situation where we have these dots, and these dots signify the joining of different conductors. Think of it like a splice where you've run 3 different wires together and you've wrapped them up and you've soldered them together so that each one is electrically connected. Same thing down here on the ground path. So what we have is a circumstance where battery power comes out of the battery to a junction and it supplies 12 volts here, 12 volts here, and then 12 volts through this load as well. By doing this, each bulb gets full 12 volts, and each bulb can now run at its optimum intensity. So across each of these loads, we have a 12 volt drop. So what we can do is evaluate this and say, yeah, this is a better circuit. This is going to give us brighter light bulbs. It's going to have a more reliable system so that if this bulb blows, it doesn't interrupt the circuit and affect the rest of them. You can have one bulb that pops and the rest of them still work. Kind of like modern taillights on a car. You might have a whole string of lights in there, and if one of them blows, you still have all the other ones. They're not affected. That's a parallel circuit. And they're always, at taillight circuits anyway, there's always a big old junction and then all the power sources split off of there. They may use a common chassis as the ground source, but you think of that chassis as the return to battery junction point as well. So if you remember from our series circuit lesson, we said that the entire circuit's amperage, the current flow through that circuit, is governed by resistance total. And that was very true in that circumstance. In this case, though, what we have to understand is there's three different circuits here. They may share a common power source, but the battery should be able to provide plenty of amperage. Each of these legs, however, has its own amperage flowing through it. So it's no guarantee that this is going to be 4 ohms, 4 ohms, and 4 ohms. In our example it is. But you might have one that's 250 ohms. You might have another one that's 20 ohms. You might have another circuit that is 302 ohms. And by understanding that each of those pathways has a different current flow, we can't just simply say resistance total is the sum of all resistances. It's not R1 plus R2 plus R3 in the example of one of these circuits. One of the easiest and most simple ways of determining our circuit resistance with parallel circuits is simply by treating each leg like a series circuit. So we can do that pretty quick. We can say that we've got 12 volts here, here, and here. And because we have 12 volts in those positions, we can say 12 divided by 4 equals 3 amps. So let's just make sure we're doing that right. We have our E over I and R. It still applies to parallel circuits. We just have to find a little bit more information before we start using it to evaluate the entire circuit. That's the big takeaway here. You can't just grab all the resistances and add them up. That's not how this works. So in our case here, if we want to manage this particular leg of the circuit, we're going to say we have 12 volts, and it's going to have a resistance of 4 ohms. 12 divided by 4, what do you get? You get 3. And so as a result, we have 3 times 4 is 12, 4 times 3 is 12, 12 divided by 3 is 4, and 12 divided by 4 is 3. So we've double checked it, we've made sure that that's true. So in each of our legs of our circuit, we have 3 amps, 3 amps, and 3 amps. So what does this mean for you and I? When we're looking at parallel circuits, we got to consider the fact that we don't add up resistances, but we do in fact add up current flow through each leg of the circuit. So it's almost like looking for amperage total instead of resistance total. So in our case here, we made it really simple by saying that each leg had 4 ohms, thus we had 3 amps per leg. All we do is simply add them up. So we have 3 plus 3 plus 3, and we get 9 amps total. So what's flowing out of our battery to the first junction is 9 amps. And then as you reach each of those junctions, it splits, it changes. So once you hit this first junction, now there's not 9 amps still flowing this direction because there's only 2 loads. Now it becomes 6, and then at this junction it splits and becomes 3. So we're not so concerned with those areas. What we would be concerned with is if you were building a wiring harness or something like that, and you did have these kinds of loads in there, you'd want to make sure that the wires on this point and this point can handle up to or a little bit more than 6 amps. And you want to make sure that the section here to here can handle 3 amps, and then everything before this first junction point can handle up to 9 amps. So let's just make sure that we can see how this works. Next thing we'll do is we'll use Ohm's law, and we'll use our E over I times R formula, and we're going to utilize the 12, our 9, and that's going to tell us our total circuit resistance. Like I said, it's not as simple as just saying 4 plus 4 plus 4. It's going to be different than that. So just to reiterate, I want to make sure you all heard that. To determine total amperage in the circuit, you can do it this way if you're doing individual series circuits and then adding up the amperage results. You can say leg 1 plus leg 2 plus leg 3 equals amperage total. And you would just put that into the I placement here when you go to do your math. Now, if we look at this, we know 12 volts, and we know what's flowing out of our battery and what's flowing back into it, into and out of that first set of junctions. So let's do the math. What is our total circuit resistance? Because right now, that's the real question. So we know we have 12 volts, We know we have a total of 9 amps, and we don't know what our total circuit resistance is. So let's determine what that is. 12 divided by 9. What do you get? You should have gotten 1.3333 repeating, because what we're dealing with is 1 1/3 ohms. And what we're looking at here is a value that is less than our smallest resistance. And that's one of the laws that we need to keep in mind, and a good way to double check our work when we're dealing with parallel circuits. Because if we get a result that's bigger than our smallest resistor, we've done it wrong. The law is that the resistance total of a parallel circuit is always less than the smallest resistance value. So it's an easy way to double check, like I said. So in this case, our total circuit resistance is 1.333 repeating ohms. And as a result, we've solved this problem. Now, we did this the easiest way possible, but it's usually the longest way possible too. There's other ways of determining this. All right, so we've trimmed up our diagram here to make a little bit of room for calculations. Now, I need you to follow along with this really carefully, because what we're doing is we're basically going to be saying 1 over our resistance value for each of these. And then you take the sum of each of those essentially decimals that we're going to create, and you add them together, and they end up here. Then to finish the equation, we have to say 1 divided by the sum of those values, and that gives us resistance total. So again, we're dealing with fairly easy to work with numbers. So when we say 1 divided by 4, what do you get? You get a quarter, 0.25. So we're going to label this one as 0.25 plus another 0.25 plus another 0.25, and that is going to equal 1 over the sum of all of these. So when we add them all up, it's pretty simple. It's like having 3/4 in your hand, 75 cents, or 0.75. So our answer becomes 1 over 0.75. So we just added them up, put them underneath the fractional line there in the denominator, and now we're going to turn it into a real number. What we've essentially done is just created some sort of a formula here. It's not important to know why we're doing the formula for our purposes. We just need to know resistance total. So in our case, we just take the sum of these after converting them from fractions to decimals, add them up, put them underneath the denominator, or in the denominator, and say 1 divided by 0.75. So if we do the math on that, what do you think we get? Do the math. So we know our answer is 1.333 repeating, and that is the same number that we got previously when we handled it like an individual series circuit per leg. Now, you can go through it that way, you can double check yourself that way just to make sure you've done it right, but the big takeaway is, again, as long as our resistance total is less than our smallest resistance values, then you know that you're doing it right. If you end up with a number that's the same as or larger than, then you know you've done it wrong, and you need to go back and double check your work. I love the idea of having this on a video so you can go through and you can see maybe where you made mistakes, and then that way you can kind of learn at your own pace. You can take your time with this. But the big thing is that doing it individually takes a lot of time. If you do the fractional version where we say 1 over 4, 1 over 4, 1 over 4, add those up, and then we say 1 over the sum of those values, we get it much more quickly. So instead of trying to figure out amperage and then determining resistance total, we don't even necessarily need amperage. We might have voltage and then individual resistances, and we might be looking for amperage. So sometimes we are forced to go through this way. There's another quick trick that I want to make sure that you all understand, and there are examples of this in the worksheets, that if we have common resistance values here, that we can do a quick trick. So let me erase our formula down here so you can see what we did. Actually, I'll just get rid of this answer section here. And I'll leave the formula up. What we have to do is we have to find the common resistance value. So in this case, our common resistance value is 4. We have 3 of them. So in these very, very remote circumstances, let me put it that way, we can just simply take the common resistance value divided by the number of legs in the circuit. So in this case, our common resistance value is 4. We have 3 of them. And so we just simply would say 4 divided by 3. It obviously goes in one time. And we're just going to be going in 3, 3, 3, and so on. So it comes up with the same answer. You can do it on your calculator. You don't have to do the long division version. You can do it where you just simply say 4 divided by 3, and what do you get? 1.33333 repeating. It's the same answer no matter which way you do it. The big key here is that this version only applies if all the resistances have the same value. And again, the way you do it is you take your common resistance value, you don't add them up, just find that they're a common value, and that value is divided by the number of resistance paths. And again, it makes sense. If you have 4 ohms per channel, you're going to have multiple pathways for current flow. Think of it like a dual exhaust on a vehicle. One of the reasons that you would put that on there is to increase flow. You might have the exact same mufflers that you had before, but now there's 2 pathways for the current flow. So while they both have the same resistance, the flow through them is different. It's reduced because there's 2 pathways for current flow. So our resistance total in our circuit is always going to be less than the common value found in each of these, or it's always going to be less than the lowest resistance value. Alright, so here's another example that we're going to be using. This example here, again, has 3 resistors in it, but now they're different values. So we could go through and we could go and treat each of them as a series circuit. That is a totally legit way of doing it. The difficulty with doing it that way is that it's cumbersome and it takes time, and you have to know a couple values first. In this case, we can't do it because we are not given our resistance, our total amperage. So that's what we're looking for. As long as you were given that value, yeah, you could go through and figure out what your resistance total is based on that, but this doesn't allow that. So in this case, we have a value of 2 ohms, 10 ohms, and 4 ohms. And in these cases, none of them are really going to be easier to work with than another, so we might as well just start by using our fractional formula. So in our case here, what we're going to do is we're going to formulate them in their fractional form. So we're going to say 1 over 2 plus 1 over 10 plus 1 over 4 equals 1 over our sum. So when we convert these into decimals, we can just easily add them together, which is why I like it. A lot of times, if you were trying to do this, there's another way to do it where you just keep them fractions, and you have to get common denominators, and you have to then add them all together. It's just more cumbersome. I like dealing with real numbers, not dealing with fractions, so this is the easiest way that I've found to do it. So you can see here that we've converted them into decimals, and we end up with 0.5 plus 0.1 plus 0.25, which gives us a value of 0.85. Once we're done with this step, we're just simply going to say 1 divided by 0.85. So hopefully you came up with the same results I did. When we look at our answer here, it's basically 1 divided by 0.85. And my answer that I came up with was 1.177. and that is our resistance total. So in our case here, I did a little bit of rounding. It was some long string, and if we round it up, it becomes 1.177. So RT becomes 1.177, and we can now use that to determine the current flow from our battery out to our first junction. Now, another quick takeaway from this is the fact that 1.177, our resistance total in this case, is less than our smallest resistor of 2 ohms. So we know that we're doing this right. If I ended up with 2.2, I'd be like, whoa, 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 something's not right here. We did something wrong, and you have to go back and backtrack. This is why it's really important that when you're doing these calculations, have a piece of scratch paper nearby so you can write down, like I'm doing here, in a sequential order so you can see where you made mistakes so the next time you don't fall into that same trap. Okay? So let's do Ohm's law now that we know our resistance total. So our voltage is 12, and that's going to go over our 1.177, and we're going to say 12 divided by 1.177. So if you've done the math correctly and you said 12 divided by 1.175, you'll have found that the answer is 10.195 amps. And our answer and our formula has given us the last detail we need to solve our problem. So I want to make sure you understand that parallel circuits aren't necessarily simpler than series circuits. In fact, they're quite a bit more complex. As a result, when we talk about parallel circuits, we have to understand that we're probably going to be doing some math, and you want to make sure you have your calculator or a cell phone with a calculator ready, and don't just wing it. I want to make sure that you guys, I really stress that to you guys. We want to make sure that we are doing this the right way because, as you can see, we're dealing with some, not necessarily easy to deal with numbers, even though our resistance values are relatively simple. One of the reasons is that we have 3 legs in our circuits, and each of the legs has a even value. So it's an odd and an even, and you end up with some weird numbers as a result. But nonetheless, if we had all common values, I want to make sure that we stress this again too, that you can make this much more simpler. So don't waste all your time if all the resistance values are the same. Find that common value and divide by the number of legs. So we're going to do another example next, and I want to make sure that we walk through a couple different examples, hopefully with some differing results. Alright guys, so we've upped the ante a little bit here with this next problem. We have 4 legs now, and we have some differing values, everything from 1 ohm of resistance up to 14 ohms of resistance for resistor 4. Don't be intimidated by the fact that we have more numbers and that we have more potential areas where we might make some calculation errors. As long as we keep following this format that we've given you, then it should be relatively straightforward. So what we do is we just simply take each of our resistance values and we say 1 divided by those resistance values and convert it into an easy to use decimal. So let's do that. Let's write it out the way it's supposed to be written and do it very methodically and step by step so we don't miss anything. We're looking at a situation where 1 divided by 7 is 0.143, did a little bit of rounding there. 1 divided by 2 is 0.5, 1 divided by 1 is 1, and 1 divided by 14 is 0.071. Now, let's add them up. We're going to say 0.143 plus 0.5 plus 1 plus 0.071, and we should get a value of 1.714. and we're going to write that as 1 over 1.714, and that is going to give us our resistance total. So if we do that next step, I'll get you guys do the math on it. 1 divided by 1.714, and hopefully we come up with the same results. So hopefully you guys came up with the same result as me. I did the math, came up with 0.583430, and if we round that down, we can make that into 0.583, just to keep things simple. So the first thing that jumps right out at me here is that our value is in fact smaller than 1, thus it is probably more than likely correct as far as our values go. It'd be kind of hard to make a mistake and then realize that, you know, it's less than it still. So we're going to continue doing our math here, and we're going to use Ohm's law now, use the E over I times R formula, that magic triangle, and we're going to say 12 over 0.583 is going to give us the current flow in our formula. So do the math. Let's make sure we come up with the same result. So my result came up to 20.583, ironically. So our amperage is 20.583. So current flow is over 20 amps in my example here. So again, we're dealing with some weird numbers. They may give us decimals of numbers in the examples. Again, don't worry about that. Just make sure that you're doing it methodically and step by step, and then saying 1 divided by the sum of all these numbers, and it'll give you the correct answers every single time. The only areas where you and I might differ just slightly, if we do this on like a Google form document, is in the rounding. So if you round back, 5 places and I only rounded back 4 places, we might end up with a slightly different number. What I want you to do is, if you do get it marked wrong on Google Classroom, make sure you put a note or a private comment to me saying, hey, I know I got these answers right, it's just slightly off of the rounding. I'll go through and evaluate it, and I'll adjust it accordingly. That way you get credit for it. For the first couple of days, though, we are going to be doing practice problems. So please feel free to go back and use this video, use the sections in this video to reinstill the knowledge that we've gone over, just to make sure that we understand it. We're all on the same page here. But that is pretty much it with parallel circuits. We deal with simply individual legs that have differing resistance values, or the same, and each leg is going to have its own bespoke current flow through it. The addition of those current flows makes up total current in our circuit, and then we just simply have to use Ohm's law. So once we've done calculating all the information related to our resistors, come up with resistance total, use your voltage and your amperage, use your voltage and your resistance total to determine amperage. You might be given amperage and you're trying to find out what the voltage is. Again, it's just Ohm's law like we're familiar with, except for we're trying to solve mostly what resistance total is, because that's how parallel circuits differ from series. We don't add them up. It is a calculation and a formula, and you're more than likely going to need a calculator for that. So thanks for watching. I appreciate you guys taking the time to do this and continue your learning, and we'll see each other again soon, hopefully.